In electrostatics, we examine charges at rest. Applying an electric field forces those charges to move, causing them to drift uniformly in a single direction. That coordinated movement constitutes an electric current. In nature, this movement is often chaotic. A lightning strike releases a massive volume of charge from the atmosphere to the Earth, but the flow is unsteady, dumping energy in a rapid, branching path. For an electrical system to be useful, the flow of charge must be smooth and continuous, similar to a steady volume of water moving predictably down a riverbed. Everyday battery-operated devices require this predictable delivery. A standard torch relies on a steady flow of electrons moving through a closed loop to keep the bulb continuously illuminated. We quantify this flow mathematically. Current, represented by the letter I, is the net amount of charge flowing across a specific area divided by a given time interval. We measure this rate in amperes. A lightning bolt carries tens of thousands of amperes. A household appliance draws perhaps 1 or 2, and the electrical signals traversing your nervous system operate in microamperes. To sustain these steady currents, we use solid metallic conductors. In these materials, the outer electrons detach from their parent atoms and move throughout the bulk structure, while the positive ions remain fixed. We harness the power of moving charge by forcing electrons to march in an orderly, steady line inside a wire. This chart shows voltage on the x-axis and current on the y-axis. In 1828, G.S. Ohm mapped this relationship and discovered that for many conductors, current increases proportionally with potential difference, drawing a straight line. The constant of proportionality that determines the slope of this line is resistance. This relationship is expressed as V equals R times I. Resistance is determined by both the material itself and its physical geometry. Having the cross-sectional area of a wire restricts the flow and doubles the resistance. To isolate material properties from geometry, physicists use resistivity. Resistivity is an intrinsic property measuring how strongly a specific material opposes current flow, regardless of its shape or size. This opposition occurs at the atomic level. As free electrons accelerate in an electric field, they constantly collide with the background lattice of stationary positive ions, creating a steady drift. The average time interval between these atomic collisions is known as the relaxation time. The frequency of these collisions dictates the inherent conductivity of the entire solid. Ohm's law asserts that this relationship holds true universally, that resistance remains a fixed constant, yielding a linear graph across any applied voltage. That mathematical model provides a tool for basic circuit design, yet real materials under varied conditions rarely maintain that straight line. This chart shows a dashed baseline representing ideal ohmic behavior, where voltage and current scale perfectly. Testing a real metallic conductor initially matches the model, but as current increases, the solid line bends, requiring more voltage to achieve the same jump in current. In this curved region, the voltage no longer generates a proportional increase in current. Thermal energy causes this deviation. High currents increase atomic collisions, which generates heat and subsequently increases the resistivity of the metal. We calculate this change using the temperature coefficient of resistivity. This coefficient measures the precise fractional increase in resistivity for every degree of temperature rise. Alloys like nichrome and manganem are used for resistors because their temperature coefficients are exceptionally low. Nichrome, an alloy of nickel, iron, and chromium, maintains its resistance value even when heated. Once a standard conductor enters that curved region of the graph, the simple V equals I times R equation fails to predict circuit behavior. Proportionality in physical conductors is a narrow operating window that collapses under thermal stress. A second failure of the ohmic model occurs when resistance depends on the directional sign of the applied voltage. A perfect ohmic circuit is symmetrical. Reversing the battery to -5 volts produces the exact same current magnitude, just in the opposite direction. This chart shows the current-voltage relationship of a diode. This semiconductor device allows current flow in one direction while restricting it in the opposite direction. On the positive x-axis, the current spikes upward. On the negative x-axis, it stays flat. The scales confirm the asymmetry. Forward current is in milliamperes, while reverse current is restricted to microamperes. The diode operates as a one-way electrical valve, allowing charge to pass through from one side while building a barrier on the other. This directional bias violates the assumption of Ohm's law, which requires resistance to remain static regardless of polarity. We use diodes to build rectifiers. These components convert alternating current, which constantly reverses direction, into direct current that flows only one way. Exploiting this asymmetric behavior allows us to direct power through circuits in ways a standard ohmic resistor cannot. The third deviation occurs when the relationship between voltage and current stops being mathematically unique. In a proportional system, one specific voltage input yields exactly one current output. This chart shows the voltage-current relationship for gallium arsenide, used in high-frequency microwave devices. As voltage increases, current rises to a peak, drops into a valley, and rises again. A single horizontal target current line intersects the curve at multiple distinct voltage points. The same electrical current can be produced by applying different voltages to the same material. Between the peak and the valley, the material exhibits negative resistance. Increasing the voltage across the material actually reduces the current. This non-unique behavior allows engineers to generate the high-frequency radio waves required for modern communications. These multi-state conductivity profiles allow for the implementation of advanced logic and precise frequency control in specialized hardware. The equations on a Cartesian plane map directly onto physical hardware. We navigate a vast scale of electrical magnitude, from the 10,000 ampere strikes in the atmosphere to the microampere pulses dictating human biology. Our domestic machinery occupies the middle ground of that spectrum. Standard kitchen appliances draw a steady flow measured in single digits of amperes. We use the linear predictability of Ohm's law to design heating elements like toaster coils, and use the nonlinear properties of semiconductors to build the logic boards that control them. These non-ohmic behaviors provide the specific switching and rectification capabilities required for integrated circuits. Modern infrastructure relies on a hybrid of these properties. Ohmic materials deliver the power, and non-ohmic materials provide the control. Designing around the deviations in Ohm's law enables the development of complex systems that purely linear resistors cannot support. Understanding why the voltage-current relationship curves and breaks provides the technical foundation for high-frequency signal processing.